Okay, here we go. So the first lesson had to do with energy in chemical systems. This was the last unit that we needed to cover in 8th grade this year. All right, now I'm going to as a prelude to some of the lessons that are coming, I want to make sure that you understand that energy is basically a sum of two things. The kinetic energy of whatever it is that we're looking at and potential energy. One of the questions that has come up from you guys actually from the quiz was how I define chemical systems. Because energy has to do with chemical systems, and not everything is the same. So you can break chemical systems into basically two types. Or you know, we can sort of break this into two worlds. You have your physical changes all right, and I'm hoping at this point in the year that this is fairly obvious to you guys. It would be like, you know, a physical change is like taking a solid of something. It could be a metal, it could be anything. I've used water as the model here, so we would be talking about ice in the case of water. All right, and a physical change would be converting it to the liquid. I think this is pretty straightforward stuff for you guys. All right, and remember that I define liquids as being, we just break a few of the solid bonds and we get to the point where the system can flow, where the stuff can flow. And once we have that, it's a liquid. So this is pretty simple. Physical change. And it should be obvious to you that the kinetic energy of the solid is less than the kinetic energy of the liquid. All right, and those kinds of relationships. So therefore, we could argue that the potential energy of the solid is less than the potential energy of the liquid. The other issue here then, like what's the other part of a chemical system? And these would be your chemical reactions. They're not the same as physical changes because we have bonds that are breaking, and we have bonds that are forming. And not all bonds are equal. And I use an example here of the combination of oxygen. I think I did this in the videos you're going to be coming up that you're going to be watching. So the combination of oxygen and hydrogen to make water. All right, and the reason I picked this reaction is because it produces a ton of energy. Light energy, heat, the whole kit and caboodle. And you guys have actually used this in the laboratory. You're literally looking at the test for hydrogen. This is what we did, you know, way back starting in August. It's the test for hydrogen gas. All right, so you know that when you stick a flaming splint into a test tube where you've got all this bubblage going on and you hear a loud plooping sound, right? That was the test for hydrogen. All right, so this is a chemical reaction that produces a lot of energy. And the way that happens is because both of the reactants are at a higher potential energy than the product that is produced. And this is because of the bonding, right? There's a difference in bonding. So if we draw the the oxygen molecule here, and then it's being reacted with hydrogen, so the Lewis formulas are going to look like this, and then the water molecule is going to look like this. basically what I'm arguing is that both the H2O, or excuse me, the oxygen and the HH here, these are at higher potential energy. So higher PE. And the product here is at lower potential energy. And since the product is at lower energy and the reactants are at higher energy, well, then some of that energy had to be released, right? And that's where this is coming from right here. All right, and so when we talk about potential energy, and I'm going to finish this, so like I promised not to go on very long. So I'm just changing screens here. So when we talk about potential energy, there's two kinds. So there's the type I just talked about that comes from differences in chemical bonds. All right, and then there is the straightforward thermal type. Thermal potential energy. Now, I realize, over here with the thermal bit, that's kind of a sophisticated term, so let me just be abundantly clear. I'm going to draw you a picture. If we have an object, like this could be a pot of boiling water. All right, and if it's boiling water, its temperature has to be 100 degrees centigrade. That's the boiling point of water, just in case for any of you that have been in the zone. This is BpH2O. All right, and if we place that next to or in contact with cold water, so this could be, straight out of the refrigerator, and your refrigerator is going to be at 4 degrees centigrade. That's generally the temperature of the refrigerator. All right, so the pot of boiling water is high potential energy. It's thermal energy, high PE. And this dude over here is low PE, thermally. So energy is, and in this case, it's kinetic, right? So kinetic energy is going to be lost from the hot water into the cold water. So this is going to be plus KE over here. All right, and with that, I think I want to stop so that we don't go on too long. All right, let me see if I can get back so I can